Hi, I'm Peter Davies, and I'm going to be talking about graph sparsification for derandomizing massively parallel computation with low space, joint work with Artur Czumaj and Merav. So I'll start with a brief intro to the massively parallel computation model, MPC, which we're going to be seeing quite a bit of it this far, I think. We're interested in graph algorithms, so we have our input graph with n nodes, m edges, and maximum degree delta. And on this graph, we're going to be doing some computation in parallel on a collection of machines. And these machines, the main restriction upon them is that they have a bound on space of S. So they can store at most S words, and here a word is, for example, enough bits to specify a node of the input graph. So to begin with, our input graph is distributed arbitrarily among our machines. We just need that one copy of each edge and each node in the input graph exists somewhere on one of our machines, and that each machine is obeying its space bound of S. And then each machine can do some computation on the data it received, and then there is a synchronous communication round in which it can send data to any other machine. And the restriction on communication here is also given by the space bound S. Because our space bound is S, we can't send or receive more than S total information in any communication round. And then we can do some more computation, and then we have another communication round. Again, our space bound S is the limiting factor for communication. And our goal here is to solve some graph problem on our input graph while minimizing the number of synchronous communication rounds we need. So things aren't quite as simple as they seem here, because often we'll be in situations where we don't actually know which machine is supposed to be receiving which part of our data. Luckily, there are existing primitives made actually for the MapReduce model, but that also apply to MPC, that allow us to do things like sorting, like prefix sums, which also allows us to compute aggregate functions over our data in only constant rounds, even if we don't know in advance where the data should be ending up. So that allows us basically to hand wave over all of this and say, whatever we're doing, as long as we obey our total space bounds on each machine, then we're okay. So I'm not going to get into the details of communication here, but essentially it's all done for us already. So the goal is just to try and optimize how we can solve graph problems in as few rounds as possible while only keeping at most S space on any one machine. Okay, the problems we're looking at are MIS, maximal independent set, and maximal matching. And these are classic graph problems. Probably everyone has seen them before. And they're also often used, or have been used in the past, as a test bed for both distributed and parallel computation models, and also for derandomization. So the goal is here to output a set either of edges or of vertices from maximal matching and maximal independent set respectively, so that the sets are independent in that no two edges in them or no two vertices in them are adjacent, and also they're maximal in that we can't add any more edges or vertices, respectively, without breaking independence. So here we have some examples on the left of a maximal matching and on the right of maximal independent sets. These are maximal because no red edges or red vertices are adjacent, and there are no other edges or vertices that could be added while preserving that property. Okay, and as I said, these have been used in a variety of distributed and parallel models, and have also been used to demonstrate new derandomization techniques, but not currently in MPC. So that's the focus of our work, really, to use these problems to explore the potential of the MPC model for derandomization. So previous results, there have been quite a few randomized algorithms in MPC in recent years. There are two major space regimes that we care about here. So space, we will consider it either to be linear in the number of nodes. Note that that's not linear in the number of edges, so we still can't store the whole graph in one machine, which is what makes it non-trivial. But linear in the number of nodes is, in most cases and in our case, equivalent to congested clique. There are some differences, but depending on how exactly your algorithms are working. But for all the algorithms we'll cite here and talk about, linear space MPC is going to be equivalent to congested clique. And so there are some results from congested clique that transfer over to here. And also we'll consider the sublinear space regime, and in fact that's what we focus on in the paper, where we have quadratically less space on any machine than the number of nodes. So we can't, for example, store a list of all the nodes in the graph, or even a node's neighborhood if the node has reasonably large neighborhood. So in congested clique and linear space MPC, there's an existing log logarithmic in delta algorithm by Ghafari et al. From last year. In sublinear space, it's a bit slower. We can only get root log delta roughly, plus a root log log n term by Ghafari and Wito. And both of these results inherently use randomization, generally to subsample some smaller graph on which you then run multiple steps of a local or congest algorithm. And there haven't so far been tailored deterministic results to MPC. There is one result on congested clique, the deterministic algorithms by Sensor Hillel, Parter, and Schwartzman in 2016. And that's log n, log delta round, so quite a bit slower than the randomized algorithms. For sublinear space, there aren't any tailored algorithms at all, but we can simulate PRAM algorithms in only a constant factor overhead, of which there are plenty. And there's a log to the 2.5n time algorithm from Han in 1996, and also a recent log squared n algorithm from Harris. These two results use slightly different numbers of machines, so I've listed them both here. But really, PRAM is quite a bit more restrictive than low space MPC. So these don't really exploit the useful properties of MPC. And that's why here we wanted to explore whether MPC is more powerful for de-randomization than previous parallel computation models. Okay, so what would we do first? What would be the first thing you try if you were trying to de-randomize algorithms for maximal independent set and maximal matching? Well, you would probably start with Luby's algorithm, the classic MIS and maximal matching algorithm. Luby's algorithm works like this. This is the maximal independent set version, but a very similar algorithm does maximal matching. You basically just replace the word nodes by edges. And what it does is each node picks a random number. The distribution doesn't really matter that much. And then each node looks at the random numbers that it chose and the random numbers that its neighbors chose, and it joins the maximal independent set if its number is lower than all of its neighbors' numbers. And then after everyone who wants to join has joined in that round, we remove all the nodes that we added to the independent set and all of their neighbors from the graph. Now you can see that this guarantees that what we get is an independent set, because nodes only join if the number they generate is strictly lower than all their neighbors, which means two adjacent nodes can't join in the same round, and then nodes that are adjacent to someone who joined get removed, so they don't join. So this gives us an independent set. If we keep running it until the remaining graph is empty, then it also gives us a maximal independent set, because we've only removed nodes that can't join the independent set and nodes that are already in the independent set. And if that means we remove all nodes, then our independent set is maximal. So how many rounds does this need to give us a maximal independent set? Well, the analysis works like this. We call nodes good if at least a third of their neighbors have degree that's at least as low as theirs. And these nodes then we can show have a constant probability of being removed in a single round of Luby's algorithm. And we can also show that the good nodes, we don't know how many of them there are, but they are adjacent to at least a constant fraction of the edges in the graph, which means that you can show that a round of Luby's algorithm removes a constant fraction of the edges in the graph at the stage where we remove the MIS node and the neighbors from the graph. Okay, so in each round of Luby's algorithm, we reduce the number of edges in the graph by a constant factor, which means after log n rounds, we've got our MIS. So how do we de-randomize this? Well, Luby himself showed how to de-randomize it using basic de-randomization techniques. The first step is to show that you can run the algorithm using only a small amount of randomness. In particular, you can run Luby's algorithm if your random choices are only pairwise independent, not fully independent, which means that you can use families of hash functions to take a very short random seed, and that suffices to give you all the randomness you need to run a random Luby's algorithm. So we still have some randomness, but not much. What do we do then? We search the space of all of these short random seeds and look for one that gives us a good property, in this case, that removes a good amount of edges from the graph. And using the method of conditional expectations, which is a kind of standard method, but I won't go into it here, we can do that quite quickly. So we've shown that we only need a small amount of randomness, and then we go and search the whole space of possible random strings quickly and find one that works. So this is what we would do if we weren't in a space-restricted parallel computation model. Where does this break in low space MPC? Well, it's the second part here, applying the method of conditional expectations to search the space of all random seeds. The reason we can't do that is because we need to know which random seeds are good. And for us, a good random seed is one that removes a lot of edges from the graph when we remove the nodes that join the independent set and the neighbors. But for a node to know if it's removed under a certain random seed, we have to know whether any of its neighbors join the MIS, because the node is removed if it joins the MIS or its neighbors join the MIS. And to know if the neighbors of our node join the MIS, we need to know which random number they generated and which random number their neighbors generated. And that means we need to store a 2-hop neighborhood onto a machine for that machine to determine whether a node leaves the graph. And that's too much space. We have possibly delta squared space here, which can be as much as n squared. And that's a lot more than our spacebound S, so this won't fit on a single machine. And if we can't do this on a single machine, then to determine this, we're going to need a load of communication rounds between a load of different machines to determine if any particular seed is good, and that's going to take us far too long. So what do we do to get around this? Well, if this was a randomized algorithm, what we would do here is say, okay, we can't fit 2-hop neighborhoods onto machines because our space bound is too low. But what if we just sample at a graph of lower degree so that we could fit 2-hop neighborhoods onto a single machine? And that's exactly what we're going to try and do here, but deterministically. So what we want is some deterministic first step where we sample a graph that's sparser than our input graph, but preserves the property that we can still run Luby's algorithm. Okay, and that's our general deterministic graph sparsification idea here. And specifically, what we want to do for Luby's algorithm is make sure that, firstly, all of the degrees of the nodes behave as they would do if we were randomly sparsifying. And secondly, these good nodes are the ones that are important. So we need to make sure that good nodes in our original graph remain good in our sampled graph. Okay, and we use our same kind of de-randomization toolkit as we were talking about on the previous slides. Bounded independence, hash functions, and the method of conditional expectations. So this might seem like we haven't really got anywhere because we're still trying to use the same techniques as didn't work before, but the difference is that this de-randomization we can do while only keeping track of properties that can fit on a single machine. Okay, so this property that good nodes remain good, and this property of node degrees not being too far away from what they would be if we randomly sampled, both of those we show can be maintained using only S space per machine. And what we do is in constant rounds in low space MPC, we can subsample deterministically a graph which is low enough degree to allow us to collect 2-hop neighborhoods and maintains the property that says that Luby's algorithm, a round of Luby's algorithm, will reduce the number of edges in the original graph by a constant factor. So we have a node in black here that we're going to try and keep track of, and we'll assume that this is a good node. And we also then have some of these orange neighbors, and these are the neighbors of lower degree than the black node. If you recall, being a good node means that we have a certain fraction of neighbors which have lower degree than ourselves. So what we need to keep track of when we are doing our deterministic graph sparsification, in this case for Luby's algorithm, is firstly that our degree decreases as we would expect, and secondly that we remain good, which means that the number of orange neighbors we have also decrease as we expect. Okay, so to do this, what are we going to do? Well, we can't store this whole neighborhood on a single machine. We need to divide the neighborhood among several machines. So this is what fits on a single machine of space S. We have a handful of the neighbors. Some of them are the orange neighbors, the ones that have lower degree, and some of them aren't. They're just normal neighbors. Okay, so we collect parts of neighborhoods onto machines, and then we just de-randomize the sampling of nodes with a certain probability. This probability doesn't really matter here, but it's enough to make sure that we expect to still see some of the neighbors on our machine stay. That's the only important part here, really. And we apply the method of conditional expectations, and we can show using a concentration bound that what we get is that the number of neighbors in total which remain, and also the number of orange neighbors which remain, is close to what it would be under completely random choices. And if it is, then that machine is happy. So these green nodes now are the ones that are remaining. If that's close to what we would expect to see under random choices, our machine is happy, and we perform the method of conditional expectations and find a seed which makes all machines happy. And what we get is that we preserve the property of a node being good, and we also preserve comparative node degrees. And we do this until our degree in the sparsified graph is low enough so that two hop neighborhoods will fit on single machines. And then we have space to de-randomize Luby's algorithm as we were trying to do before. So that's the idea. I'll now show what it gives us. So these were the previous results for linear and sublinear space MPC. And what we get are that in linear space MPC congested clique, we remove a factor of log n and just get down to log delta. And we have a similar bound in sublinear space MPC, but with a log n term, which there is some evidence that it's conditionally essential. I should say that these algorithms actually need a second stage for when the input graph already has low degree, because otherwise naively de-randomizing Luby's algorithm would give you a log n round complexity. To get log delta round complexity in linear space MPC, we use an existing result by Senza-Hillel, Artur, and Schwartzman. And in sublinear space, we do round compression. So we collect balls of a certain radius onto machines, and then we simulate multiple rounds of Luby's algorithm in a single MPC round. And doing so, we get the log n factor down to this log delta factor here. So what are future directions for work? Well, we would like to hope that this deterministic graph sparsification framework can be useful for plenty of other problems. We'd have to change exactly what property it is that we're checking still holds when we're de-randomizing the sampling of a graph. We do have follow-up work that's going to be appearing at PODSI this year applying this to coloring, but hopefully there are also many other problems where an approach like this would work. Secondly, I haven't really talked about total space here, but as well as the space bound on a single machine, we also want to make sure that we don't use much more space in total over all machines than it takes to write and read the original input graph. So here we have optimal dependency on the number of edges in the input graph, but for sparse graphs, we have slightly suboptimal dependency on the number of nodes. So we'd like to know whether that can be improved without hurting our running times too much. And finally, all of our algorithms here still have this log delta term in the round complexity. We want to know if there are any problems for which we can get sub-logarithmic round algorithms. Good candidates here might be coloring or maybe approximate matching. These problems are usually considered to be slightly easier, so maybe that would be a good starting point. Okay, so that's all for this presentation. Thanks for watching, and hopefully I'll see you at the discussion session to answer any questions. Thank you.